Okay, now it's recording. Okay, so now we can do a share screen. All right, so we're going to have basically it's defined as a tutorial. And so that means that after that, you're going to get your problem set. I'm starting to look, we still have 5 more weeks of the semester, and I won't be able to cover everything I was hoping to cover. But again, I don't think it matters that much, because what I care about is that the things that we do cover will be clearly, clearly understood. That's more important for me. As you know, if there is some part of the chapter which we do not cover, then you can always go to the textbook and read it, provided you understand pretty much everything else. There's not much point in going fast over things and then you won't understand well enough. Okay, so last time there was one part that I wanted to complete. So just a quick recap. Before we go on the tutorial, so we spoke where we were speaking about the Dirac equation, right? And we spoke about the spins, the Dirac spinor, the fact that the Dirac equation gives rise to 2 spin 1/2 states and 2 spin 1/2 antiparticle states, so a total of 4 states. We spoke about the helicity, right? We spoke about antiparticles. And the parity operator. And then we spoke about the spin and helicity states. Right, we define helicity H to be the projection of the spin in the direction of motion. Right, and we said that helicity is a constant of motion, so it's conserved, but it is not Lorentz invariant. So if you go from one frame to another frame, 2 observers would not agree on the helicity. And then we defined and then we found the eigenstates of the helicity. And then we defined the chirality, which is kind of related operation. This is the handedness, right? Chiral comes from hand, which is a quantity that is Lorentz invariant. Now the two merge in the specific case of particles that travel at the speed of light. So it can be a bit confusing at the beginning. How can it be that I said that the chirality is not conserved, but it merges with helicity, which is conserved? And the reason is that the chirality operator gamma 5, right? It does not commute with the full Dirac Hamiltonian, or HD gamma 5. It's not 0, but if you look at HD, the Dirac Hamiltonian, right? It's alpha dot p plus beta m. Then you see that when E is much greater than m, so when the particle travels at velocities which are close to speed of light, then HD, in this case, is alpha dot p. And this does commute with gamma 5, because gamma 5 and alpha is equal to 0. And so HD and gamma 5 is equal to 0. But gamma 5 and beta is not 0. And then the last point that I wanted to mention to you regarding the Dirac equation, actually I wrote some more, but I see we don't really have time, so I don't want to spend more time on that, is the chiral projection operator. Right, so basically any general spinor that we have, we can decompose it into a right and left-handed components of the chiral representation using the chiral projection operator, right? PL and PR. So we define two operators. Right, PR is 1/2 1 plus gamma 5, and PL is 1/2 1 minus gamma 5. And then we wrote down the properties of the gamma 5 matrices last time, right? So it's pretty much straightforward to show that these two operators, PR and PL, satisfy everything that you'd imagine from a projection operator, right? For example, so using the properties of gamma 5, then we have that PR plus PL is 1, PR is just PR, right? PL is just PL, and PR is just 0. Which means that every spinor that we have, we can always write it as a sum of left and right-handed spinors, right? So if we have any spinor, Dirac spinor U, satisfying the Dirac equation, we can always write it as R UR plus AL UL, which is just the right-hand projection of U and the left-hand projection of U. Of course, AR and AL are just complex numbers, right? Complex coefficients. Now we'll find it useful because as of next week, I'm going to start introducing the Lagrangian of the standard model. And then this will play some role. Now, if we write the Dirac power, if we use the Dirac Pauli representation, then we can write down then we have that, again, just plugging in the gamma 5, it's pretty straightforward to show that it's just, it's a small exercise. It's 1/2, then it will be 1, basically 4 units, right? 1, 1, 1, and 1. Then the PL is 1/2 of 1 minus 1 minus 1 and 1. And it's pretty straightforward to show that the outcome of the operation of the projection operators on the eigenstates of gamma 5. So PR UR. So applying, maybe I should write it down. Applying the projection operators on the eigenstates of gamma 5 is, PR UR. You can guess the answer, right? It's just UR. PR UL is just 0, and then PR VR is 0, and PR VL is VL. Of course, the same would be for L. PL UR is 0, PL UL is UL, PL VR is VR. Remember, V are the eigenstates of the antiparticles, and PL VL is 0. This is just basic algebra. There's nothing really to worry about here. And one last comment, there was a question I was asked about these presentations last time. I said that we're using the Dirac Pauli representation for the gamma matrices because it's most convenient and mostly useful. But I told you that there are other representations as well. It's of choice, right? It's a convenient. So I mentioned two. There is the whale, or also known as chiral representation, which is good to describe, good, handy to describe chiral eigenstates. or chiral particles, and there is the Majorana one, Majorana representation, which was invented by Majorana to best describe fermions which are their own anti-fermions. We don't know of any such particles because, you know, they must have the same charge, so that means that they are charged less. There is still the option that the neutrinos might be Majorana particles. And then the question I was asked is whether these represent different particles. And the answer is no, they cannot. Because all these particles solve the Dirac equation, and the Dirac equation represents spin half particles. So that really means that the different representation simply means that you know, there is some unitary matrix which you know, transform between the presentations, right? You can always write down Majorana as some, you know, unitary representation of U times gamma I Dirac-Pauli times U dagger. So it's a linear combination, really, of states. Yeah, that's, so basically that means that you can think of any Majorana particle as a linear combination or superposition of two Dirac particles. Well, it's not Dirac particles, it's the wrong term. In any way, all of these particles represent, all of these states represent eigenstates or particles which are solving the Dirac equation, namely spin half fermions. Any questions? Any questions? Okay, if not, then I'm going to go to today's topic. Today is basically defined as a tutorial, and again, it's going to be a long tutorial because I want to cover two different aspects which we partially discussed. One is called the Isospin Symmetry, and the second is the flavor in the CKM matrix. CKM is Kabibo, Kobayashi, and Masakawa. So today's topic is Isospin Symmetry. Flavor and the CKM matrix. So it's really two topics. Okay, isospin. Let's begin with an isospin. This is a symmetry, right, which is related to the strong interaction. Isospin is a symmetry related to the strong interaction. That basically is used in explaining how the individual quarks are grouped together into baryons and mesons. Okay, so it has some historical origin, right? It was initially discovered that the masses of the proton and the neutron are nearly identical. So historically, right, the difference m proton minus m neutron, they're not exactly identical, right? But they're nearly identical. It's about 0.1%, 1 in 1,000. And the binding energy, right, of the different combinations, proton, neutron, 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 proton, proton, in the nucleus is also nearly identical. Which means that since this is done via the strong force, that means that the strong force potential is nearly the same for the two protons, two neutrons, and proton neutrons. And the same, you know, when you do scattering experiments, neutron, neutron, proton, proton, they're the same up to the obvious charge difference. Right? Now, we're not used to think of protons and neutrons as being identical particles, and that is because, of course, there is a difference in electromagnetic interaction and also in the weak interactions, right? There is this beta decay. Neutron can decay into proton, but not vice versa, right? But when it comes to strong interaction, they are nearly identical. So if there was no electromagnetic or weak interactions in nature, then it would be very difficult to distinguish between them. They would still be distinguishable because, you know, there is a difference in mass, right? A small difference in mass. So that's why we say it's only an approximate symmetry, not an exact symmetry. But they're identical. So there is there are differences between proton and neutron via EM and weak interactions. But not, or nearly not, strong interactions. Right, modulo the mass, modulo the small mass difference. Which means that the symmetry is only an approximation. Also, it's a pretty good approximation.
Yeah. Can one say, at least from a classical point of view, that the difference between the masses, the rest masses of the proton and the neutron, come from the electromagnetic interaction between the up and down quarks?
No. No, it's got nothing to do with the electromagnetic interactions. It's got to do with the strong force and the way the goes together. Okay, now we have a symmetry here. Now the symmetry group, I didn't get to you with the symmetry. I'm thinking if whether it should be a full tutorial or not. Symmetry group that is called SU2. And the symmetry group is SU2. That's called special unitary 2. 2 is the 2 by 2 matrix. This is the same symmetry group that describes the spin. That's why we call it isospin. But there is no connection between the isospin and the spin, apart from the, having the same mathematical structure, which is the origin of the name. The same mathematical structure as the spin, but otherwise they're not connection. They're not connected. So just in this case of the regular spin, since the mathematics is the same, then we can use exactly the same prescription that we derived for spin, which is the same prescription that we derived for, angular momentum, which I believe you've seen. So just in the case of a regular spin, we can describe isospin by two numbers, right? I, which is the total isospin, and I3, which is the component of the isospin vector in a given direction. So, we can describe, isospin identical to the spin, identical to the spin, I and I3. Right, this is a state which describes the isospin, which in our case will be the proton and the neutron. So in this picture, right, the proton and the neutron are two states of one particle, which we denote as the nucleon. So P and N are two states, so it's the same particle, right, of the same particle, nucleon, right? And we assign to them an isospin doublet, which is called I equal 1/2, both of them. That means that the proton, right, I will describe it as I equal 1/2, and I3 also equal 1/2. And the neutron, I will describe as the total isospin of 1/2 and the I3 of minus 1/2. Now, this was done before the discovery of the quarks. Now, once, initially people didn't know that this proton and nucleon has internal structure, right? But when people discovered the quarks, well, it became clear that the symmetry between the proton and the neutron is, identical to the symmetry that there is between the up and down quarks, right? Because we know that P is made of 2 ups and 1 down, and N is made of up and 2 downs. So we can define the up and down state in the same way as we define the proton and neutron state, and use these to construct the hadrons, right? The baryons and the mesons, right? So we can extending the isospin symmetry to quarks, right? We can define, right, the state of an up quark, again, 1/2, 1/2. Also, you know there's 1, 0, and the down quark of 2, 1/2 and minus 1/2, which is the 0, 1 state. So if the up and down quarks were truly indistinguishable, right, then the flavor independence of the QCD interaction could be expressed as an invariant under some general unitary transformation, right? We could write down, so if up and down quark states are indistinguishable, right, that's the meaning of a symmetry, are nearly indistinguishable, then the flavor independence of the QCD interaction right, should be invariant under a general unitary transformation, right? We can mix them. So if I write down U prime, D prime is some unitary transformation of U and D, I get a state which is a combination of both up and down states, but I don't have a way to distinguish it because the up and down states are indistinguishable, right? U, right, it's a 2 by 2 unitary matrix, right? So U dagger is I. So I can write this straight. It's a unitary matrix. I can always write it in the form of the exponent. Alpha dot sigma. right? Sigma is the same Pauli matrices. I have a question to you. I just made a statement. Nobody said anything. How many of you feel that you understood what I said? That if I have a 2 by 2 unitary matrix, then I can always write it as in the form of an exponent. One understood? Who else understood? Half understood, not that 1.5 understanding, 2.5 understanding. There are 2 people who didn't raise their hands. Guys, I definitely expect if you don't understand, stop me and say, look, please explain, or please make a tutorial about it. It's not a trivial statement. If you've learned it, if you've seen it, then you know that it's true. But if you've never seen it, then it's, you know, don't try to be polite and say, oh. You with me, guys? Those who did not raise your hands. Yeah? I'm awaiting your answer. Yeah?
I'm with you.
Okay. So, it's a structure spin. So, you know, similar to the spin, then I have rotation in the isospin space. I rate it in terms of the Pauli spin matrices, right? I would say that these Pauli spin matrices are the generators of the SU2 symmetry group. Similar to the spin, identical, right? Rotation in isospin space is written, rotations are written in terms of Pauli matrices. Right? Is generators of SU2 symmetry group. So, for example, let's take one example, right? We can show that if we rotate an angle of pi around the y-axis, this transforms the up state into a down state, right? And vice versa. Like rotate by angle pi along the y-axis, right? U by y, acting on the up state. Now, what is that? That just means cosine pi over 2 minus I sine pi over 2 times sigma y u. I write it down as just minus I, right? Sigma y is 0 minus I 0. And then u is 1, 0. So this just gives me a 0, 1, which is, of course, the down state. If I take the down, if I rotate by pi along the y-axis, the down state, again, it's a minus I, 0 minus I 0. The down state is a 0, 1. That's actually, I'm going to get minus 1, 0. So it's a minus the up state. So what did we find, right? That when we make a rotation by angle pi along the, you know, in the isospin space, right? Then we replace I3, right? 1, 0 becomes a 0, 1 and vice versa. But we also add a factor of minus 1 to the power I minus I3. That's easy to show. Right? The rotation in pi angle pi the isospin space, in the isospin space replaces I3 and adds a factor of -1 I minus I3. So this is an example, the PN state, right? It's an example of an isospin doublet, right? So in particle physics, when we say isospin multiplet, right, these are families of hadrons with approximately equal masses. Now, all particles within the multiplet have the same spin, parity, and baryon number. But of course, they can be different in electric charge. So this is an example. PN system is an example of a doublet. So isospin multiplet, right? The families of hadrons with approximately equal masses. This is all have the same spin, parity, baryon number. But not the same electric charge. Okay, now we want to study mesons. What are mesons made of? Do you remember?
Quark, anti-quark.
Very good. Quark, anti-quark pair. So if we want to describe mesons, we also have to define the isospin doublet for the anti-quarks, right? Because we want to combine, these doublets of, doublets and anti-doublets, right? To construct the observed states of the hadrons. This is going to be done using the Klebs-Jordan coefficient. How many of you have learned the Klebs-Jordan coefficients? And this comes in addition of angular momentum. 2. What about you two guys? There are 2 that did not. Do you know what is the Klebs-Jordan coefficients? No? Answer my question.
Yes.
Yeah, you did, but there are 2 people that don't speak. No? You don't want to tell me? Okay. So what we want is a way of finding, describing the anti-quark such that they will perform the same way as parts if you want to put them in a doublet. Right, so to put anti-quarks in a doublet, we want the anti-quark doublet to transform in the same way as the quarks. So the way to define the anti-doublet is with this extra minus sign. So we define the anti-doublet. So the anti-down is going to be the half and half. That's going to be with some minus sign, minus 1, 0. The anti-up is the 1/2 minus 1/2. Let's be with a plus 0, 1. So I added this extra minus there because when I do it like that, it ensures that when I make a transformation of the antiquarks, they will match exactly that of the quark. So that's the transformation. Of the antiquarks matches that of the quarks. So you along the y direction, the down, this is minus I 0 minus I 0, the minus 1 0. That's a 0 minus 1. So that's a minus up. The mu the up minus I 0 minus I 0 0 1 is again it's a minus 1 0. So this is the down. Anti-down, right? Now I didn't really prove it. I just gave you one example. But you know, this definition ensures that any transformation that I make, any unitary transformation, not just by pi along the y direction, but by any angle along any direction, ensures that for any such transformation, this doublet for any transformation anti-doublet, doublet, Q anti minus du, right, transforms exactly, right, the doublet Q. Not sure that you can see it right away from this definition. I think you have to play a little bit with that. The reason I say that is because when I saw that first, I had to play a little bit myself until I got convinced. So please do that at home. So in terms of the isospin assignment, I3 is in terms of I3, right? We have I3 of U is plus half, right? I3 of D is minus 1/2. I3 of anti-U quark is the minus 1/2, and I3 of the minus anti-D quark is plus 1/2. So if you want to study the meson states, right, we now have to add the doublet and anti-doublet, right? So when we have the doublet and anti-doublet for meson states, so for meson states, right, must add the doublet plus anti-doublet. You can have either I equal to 1, I total, right? Total isospin equal to 1 or equal to 0, right? So if we have I equal to 1, right? We have three options. Right. Either the I3 is a 1, or it's a 0, or it's a -1. Now, 1 and 1 means the minus up and down, or up and minus down. Right? Each one have an I3 of +1/2. Right? Up and a minus down. We call that the pion plus. It's a pion plus particle. 1 and -1, of course, would be the down and anti-up, which is, of course, the pion minus. And here we have to have a linear combination. And we can make two linear combinations. One will be symmetric, which will place with respect to exchange of particle, antiparticle, and one which will be anti-symmetric. Since these are anti-symmetric, I can use the anti-symmetric part here, and this will be 1/√2 of up, anti-up minus down, anti-down. I call this the pion 0. I also have the symmetric part, which will be associated with the 0. So the I equal to 0, I have the 0, 0 state. This will be the symmetric part, 1/√2 of up, up part, up, anti-up, plus down, anti-down.
Huh?
Yeah.
If you have a particle that can be an up, minus up, and down, minus down, doesn't that annihilate? Won't they annihilate each other?
No. No, it's a quark, quark, anti-quark. They don't annihilate. No, they produce the mesons. This is how a meson is made of, right? A pair of quark, anti-quark. What would annihilate if you have a lepton, anti-lepton, or baryon, anti-baryon? Whatever quark, anti-quark, they do not annihilate, no.
Thank you.
Okay, we call this the Eta particle. It's not a particle. It's called the Eta. Eta meson. So this is symmetric. Right?
So the quark and antiquark are opposite in all their properties, like color and charge? It's the same color up and anti-up?
And no, they don't have to have the same color. That's why you can have multiple. They have different colors. You have a combination of colors here for the pions.
So if they had the same color and anti-color, then they would annihilate?
No, as far as I know, but I have to check that. Not to be honest. The best knowledge they don't annihilate, but let me check this point and return to you on Thursday.
So when you said, I know, a month and a half ago, that the initial pion is U up, anti-up, minus down, anti-down, the reason was that it has to be an eigenstate of the isospin. And this is the only way you can create from up, anti-up, and down, anti-down, an eigenstate of the isospin. That's why they're not just up, anti-up, and down, anti-down, but these superpositions.
Yes, it's a little bit more complicated because I skipped this part. So let's go back. In quantum mechanics, you learn about the ladder operators, right? So if you take the ladder operators that take you one, it's identical here to what we do. The only thing which is different is that there is an opposite sign to the spin, but forget about the sign. So you take the eigenstate and then you take the ladder operator and you raise it. So if you take you can do the same thing here, right? Because I plays the role of the total angular momentum and I3 plays the role of the angular momentum in a given direction. So when you take the ladder operator and you operate on the pi minus, you get the pi 0. It's actually, you can find it in many textbooks. I mean, I'm using the textbook. I'm following mostly, not all of it, but I'm following mostly the book by Thompson. He actually does give some section about explaining these ladder operators. I skip it just because of lack of time. Same reason why I did not do the Fermi-Golden rule, because it's relevant for quantum mechanics. It's identical to what you learn in quantum mechanics.
2 more small questions.
Yeah.
When you say antisymmetric and symmetric, corresponding to what symmetry, to what operation?
Change of the particle, antiparticle.
Oh, okay. So under what you call C, the charge. Okay, and you didn't write eta naught, but eta, just because there is only one eta, so it's clear.
Yeah, it's just because there's one eta here. Okay, any further questions? Well, okay, I have to rush. Well, don't have to rush. I want to finish 2 parts, and we're already halfway through the lecture. And I'm not finishing the first part yet. So, okay, we know this is for the proton neutron, right? So we have these up and down quarks. We know that there are other quarks. So just a few notes. Right, so if we have quarks that are not U and D, we simply assign to them I equal to 0. For quarks which are not up and down, we put I equal to 0. Now we can simply use direct isospin for hadrons. Right, so if we have, for example, K, the count plus is U and S bar. Right, that means that I is 1/2. Right, the B0 particle, the strange B0 particle, should be anti-S again. That will give us I equal to 0. So there are no up and down quarks here. The lambda particle, lambda 0, right, is the UDS. That will mean that I is equal to 0. And the delta particle, delta plus 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 is U and U, will give us I of 3/2. Now, okay, so the formalism works for mesons. It will work for interaction between different nuclear states, such as the proton-proton and neutron-neutron. The I and I3 are conserved in the strong interactions.
You write here I, do you mean I3 or I?
No, I need I mean the total I. Conserved.
So could you explain why is it the case for the lambda naught?
That's a good question. Yeah, well, the simple answer is because you're adding angular momenta, and it's a vectorial addition. If there is an easier way of seeing that, then I don't see it right away at the moment.
So perhaps to go back to Clebsch-Gordan, thanks.
Yeah, it goes back to the so it's vectorial. Of I, right, of the total isospin. I want to give you an example, which you'll see in 1 second. So I and I3 are conserved in strong interactions. I3 is also conserved in electromagnetic interaction. And we're actually going to use this to analyze the probability of certain processes. Now, just as a comment, there is another symmetry which is called the weak esospin. I'm not going to say anything about this symmetry. It is related to the unification of the weak and electromagnetic interaction. Here I just said something about it. And I only mention it that you know you might read it in a textbook so you don't get confused. So there is this thing which is called the weak esospin. Related to the unification of the weak. Again, it's got nothing to do with the esospin we're discussing here right now. So let's give an example. So we use, so example, a question, use isospin properties to evaluate the scattering rates of the proton plus antiproton going into 2 pions. How do we handle this problem? So step number 1 is to realize that what type of outcome can get out of this interaction.
Please repeat.
What are the possible outcomes of the interaction?
Pion plus minus or pion 0, 0?
Yes, very good. Very good. So electromagnetic charge, right? Observation means we can only have P plus anti-P goes into 2 pion zeros, or P plus anti-P goes into pi plus and pi minus. Now, let's look at the isospin representation. So we said that the P would be 1/2, 1/2. And anti-P would be 1/2 and minus 1/2. The pion plus is a 1, 1. The pion minus is a 1, minus 1. And the pion 0 is a 1, 0. So for the initial state, right, it's made of 2 P and anti-P. It's going to be 1/2, 1/2, 1/2 minus 1/2. So 2 options, right? 1/√2 of 1, 0 plus 1/√2 of 2 of 0, 0. What we really take here is from the Klebs-Jordan coefficient. So if you're not sure, just go to the Klebs-Jordan table. And the same we do for the final state. Now we have 2 options, right? Either it's a pi plus, pi minus, which is 1, 1, 1, minus 1. So again, using the Klebs-Jordan coefficient, that is equal to 1/√6, 0 plus 1/√2, 1, 0 plus 1/√3, 0, 0. Or we can have the pi 0, pi 0. Because again, it's a 1, 0 1, 0. And again, looking at the Klebs-Jordan table, this is equal to square root of 2/3 2, 0 plus, oh, sorry, minus 1 over square root of 3, 0, 0. All these numbers, so just the Klebs-Jordan tables. Is that clear to everybody? Hopefully. Okay. So how do we proceed? So we know what is the initial state. We know what is the final state, right? So basically we have some operator, O, right? Some operator, O, right? Which is the interaction operator. Right? So scattering amplitude, right? So what we care about, M, is just the final O, an initial state. And we simply need to write down this. Well, we're interested in, the question was, what is the probability of getting each of these outcomes? So we know that the isospin eigenstates are orthogonal to each other, right? Isospin eigenstates, we use eigenstates are orthogonal to each other. And we know that if the interaction is to conserve spin, or isospin conservation means that O and I, O and I3 are conserved. So O does not change the isospin state. So can use only the non-vanishing terms. So only the non-zero terms. Be lazy. We have that the M plus minus, right, is the pi plus pi minus O P bar. So again, P bar, I have a 1, 0 and a 0, 0. So the 2, 0 would give me a 0. I just have the 1, 0 and the 0, 0. So here I have 1 square root of 2 over 1 square root of 2. That's 1/2. And here I have 1 over square root of 3 over 1 over square root of 2. That's 1 over square root of 6. So that means I have 1/2, 1, 0, 0, 1, 0, plus 1 over square root of 6, 0, 0, 0, 0, 0. Let's just denote this by A1 and this by A0. We have 1/2 A1 plus 1 over square root of 6 of A0. And then similarly, M00 is just pi 0, O P bar. It's minus 1 over square root of 6, 0, 0, O, 0, 0. So this is minus 1 over square root of 6, A0. Now it's the same A0, though we're representing, the 0, 0 represents different particles really, when you think of it here. But they come from the same isospin multiplet, so I can use that. So now the cross section, right, is proportional to the square of the amplitude and the phase space. Now, since the mass of the pions are much smaller than the masses of the proton, then the phase space are nearly the same. So I don't care about the phase spaces. And in any case, we look at the ratio, so we don't really care. So the ratio of, which is just the cross section of the P plus P anti-pi goes into pi 0 plus pi 0 divided by the cross section of P plus anti-P goes into pi plus pi minus, just m00 squared divided by m plus minus squared, so just 1 over 6 a0 squared divided by 1 over 2 a1 plus 1 over square root of 6 a0 squared. Now the reaction occurs via some intermediate state, that's called the resonance state. So if the reaction occurs via an I equal to 0 resonance, if the reaction occurs via I equal to 0 resonance, right, then obviously A0 is much greater than A1, and you get that R is approximately 1. And otherwise, if it occurs via I1 resonance, I equal to 1 resonance, that gives that A1 is much greater than A0, and then R is around 0. Okay, you got the idea? Yes, no, maybe? No questions?
In past classes, we checked parity eigenvalues and charge eigenvalues, etc. Shouldn't we do the same here?
Again, I don't understand the question.
Last week, when we tried to check such process, we started by finding the parity eigenstate.
Correct.
Value, for example.
Mm-hmm.
Here, you just tell us that it's all right in both cases?
No, I didn't tell you that. I just gave you an example of the use of this isospin to calculate the probabilities. Last week, I gave you parity.
One still needs to make sure that other symmetries are preserved.
Yeah, of course.
Okay.
Okay. Now I want to use the next half an hour or so that we have to speak about the flavor change in the weak interaction. So-called the Jim mechanism, after Glashow et al. Okay, so now I'm going to say a few words about the weak interaction. So we know that the W plus minus bosons, they do carry electric charge. So they can change the flavor of both the leptons and quarks. W plus minus carry electric charge. Just change the flavor. Of leptons and quark. Now, when you're connecting W plus minus to a lepton, right, the lepton family number is conserved. But there is no such constraint with the quarks, right? So the W plus minus can connect quarks from different generations. but not leptons, right? W plus minus can connect quarks from different generations, but not leptons. So, we cannot have a decay like I minus go into neutrino mu. That is not allowed, right? But we can have an interaction that the S quark becomes a U quark, right? We can have something, not just that, right? But as part of a larger interaction. This is allowed. But of course, it's going to have a smaller probability than that of an S quark, than same generation interaction. So the probability of a down quark turning into an up quark is much larger than that of an S quark turning into an up quark, but this is still allowed. Now we said that the coupling constant of a process is a process that involves quarks from same generations and then from different generations. So coupling constant of a process is different for processes that involve quarks from the same generation and from different generations. Maybe I should say then, not and. Now, this can only happen by the charged weak current, right? There is no flavor changing neutral currents. That's called FCNC. FCNC is a flavor changing neutral currents. Neutral currents. They have never been seen in experiment. So how do we describe that? Well, the easiest is to start with, first two generations. We'll include the third one in a few minutes. So the mixing between the quark generations, we can describe it by introducing a linear combination of, let's say, the S and the D quarks, right? So we can describe the mixing between the quark generations by introducing a linear combination of the S and D quarks. So we can say, D prime S prime is cosine theta C sine theta C minus sine theta C and cosine theta C of the D and S. Now the C here, let's see on a Weibo angle. Two B's. So, basically, what we have is that the charge weak interaction can connect the up and the D prime, or the S and the C prime, right? So if we expand, then we get that the U quark, right? We can write this W times D prime, which is, W D cosine theta Cabibo plus W S sine theta Cabibo. So we have a way of, treating the two different generations of the quarks, right? The D and the S, in a way that allows both of them to interact and produce a U up quark. So we can have this interpretation as if we have three different coupling for the charge weak interactions. So the interpretation there are three different couplings. For the charge weak interaction. Right, so we have the coupling of the weak for the leptons. And then the same coupling, but with the cosine theta Cabibo with the same generation quarks. Then GW times sine theta Cabibo is the different generation quarks. Now, theta Cabibo you can find experimentally by measuring the coupling constant between the quarks of the same generation, the up and down quark is different generation, such as the S and the up, right? So theta Cabibo is about 14 degrees. This is an experimental result. So the ratio between the cross sections, right, sigma of, let's say, up decaying into S versus sigma up decaying into a down, right? They should go as G weak squared sine squared theta Cabibo divided by G weak squared cosine squared theta Cabibo, which is approximately 0.05 divided by 0.95, or about 1 in 20. Now, this is sort of an historical way of describing it. And the reason why I use the S is because the S was discovered before the C, the charm quark, right? So there was a time, I think that when Cabibo worked it out in the 1960s, people didn't know about the existence of a charm quark. They knew about the U, the D, and the S. Now, let's expand the picture, right? I mean, there's nothing that prevents us from expanding this picture to 3 generations. So expanding this picture to 3 generations. Right, we have the D prime, S prime, and the bottom prime, right? You can write this as a set of numbers, right? V up, down, V, C, D, V, T, D, V, U, S, V, C, S, V, T, S, V, U, V, V, C, V, V, T, V. Right, it's a D, S, and B. That's known as the Cabibo-Kobayashi-Maskawa. This is the CKM matrix. The Cabibo-Kobayashi-Maskawa. The CKM. Now it's a unitary matrix. course, right? It really described us what's the probability of quark of one generation to interact with the quarks of another generation, right? So the Vij, these are really complex constants that there is nothing in the standard model that tells what the values of these V's are. Right? So Vij, these are just complex constants. Not determined by the standard model. So it's only experimental. So when we have experimental measurements, VCKM approximately, I'll give you the values, just get a feeling. So obviously the diagonal which represents interactions with the same generation is the highest, right? So it's going to be 0.974. It's going to be 0.225. This is going to be 0.009. It's going to be 0.225, 0.973, and 0.040, 0.004, 0.041, and 0.999. So the diagonal elements, which represent the same generation transition, are the highest, right? So if you have a bottom quark, it will most likely decay into a top quark, right? The transition between the third generation, you know, the third line or row here, and the first two is very small. Now, if we just take the first two rows, right? There's 2 by 2, and we get back the Kabib matrix. Now we said, well, it is said that B prime, S prime, and B prime, those are called weak eigenstates. And the D, S, and B, these are known as the mass eigenstates. Now, again, it was introduced as such, I think, from mainly from historical reasons. Well, no, this is not from historical reasons, because this contains the B. So at that time, they knew about the bottom quark as well. Now, okay, the reason why I said that is because I want to introduce to you, you know, a nice prediction that was given. It's called the G mechanism, which was a historical way of predicting the existence of the charm quark. So the G mechanism, GIM stands for GIM. That goes as Glashow, Iliopoulos, and Mayani. Iliopoulos, Mayani. Mechanism. It's a prediction of the C quark charm. In 1970, 70 or 71. Okay, I'm not totally, I don't remember exactly if it was in 70 or 71. You can Google it. What they did is they look at the decay of the count, the K0. So K0 decays into a pair of muon plus and muon minus. Now, at the time that they wrote it, there was only known the U, D, and S quarks. So there is only one leading order diagram with the amplitude, the leading order diagram. Where looking something like that. So you have the count 0 is made of the D and an S, D and an anti-S. Right. So they decay into the muon plus and muon minus. I'll write it like that because it's easier to demonstrate what I want to say. It will go into a mu plus and mu minus. And that happens via the weak interaction. So we have one exchange of a W, and that will turn into an up. And the second exchange of a W, and plus. That will turn into a neutrino mu, of course. Let's see how the D and S bar. So the couplings here, it should be cosine theta Cabibo, because it connects the down and the up of the same generation. And this would be the sine theta Cabibo. Right, so the matrix element should be proportional to G weak to the 4. So we have 4 vertices times cosine theta Cabibo, sine theta Cabibo. This is something which you can measure. We know what is theta Cabibo. We know what is G weak from weak interaction, from leptonic interactions. So you could calculate theoretically what is the expectation, what is the cross section, basically. But it turned out that experimentally, the branching ratio is much, much smaller. It nearly never happens. You know, experimentally, the branching ratio is the fraction of in which this decay happens versus the rate in which other possible decay happens, is much smaller. 6.84 times 10 to the minus 9. That is much smaller than theoretical predictions. So the solution made by these three guys, Iopoulos and Mayani, was that maybe there is another quark, a fourth quark, which is a charm quark, whose coupling to the S and the D carry these factors of cosine theta and minus theta. Right? So we have right. So we have the Gim solution, new quark is a charm. So if we have the up and down, right, up and down coupling to the W, this will be cosine theta Cabibo U weak over square root of 2, right? And the up and strange. This will be G weak over square root of 2 sine theta Cabibo. Then they suggested that there is also this anti-charm. Maybe connected to the weak. And here they put a minus sign, so this will be a minus sine theta Cabibo. G weak over square root of 2, and the charm with the S. So it will be a G weak over square root of 2 of cosine theta Cabibo. So you end up having another diagram like that. Nope. But rather than 2, we have here C. Then we have here a minus sine theta cabibo and a cosine theta cabibo. So the amplitude here, M2, right, will be minus G weak to the 4 cosine theta cabibo sine theta cabibo, which would cancel out M1. They nearly cancel out, but not exactly canceling out because the mass of the charm quark is not the same as the mass of the up quark. But then the total rate, then we end up, then the total rate for the count decay into a pair of mu plus minus should be proportional to M1 plus M2 squared, right? So M K0 goes to mu plus mu minus. So it's just M1 plus M2 squared, which is nearly 0. So what was their suggestion? It's kind of nice mechanism. Okay, the last few minutes, I want to make one more thing, an example or question. That is, what is the main decay channel of the W boson? Is it hadronic or is it leptonic? Okay. Let's calculate that together. Any questions, by the way, so far? I'm rushing because I'm running out of time. So feel free to stop me if you have anything. Okay, let's see. Let's try to answer this question. So if it's a leptonic, if the W, let's say plus, would go into a lepton plus neutrino. Right? What do we know about leptonic decay? We know that there is no generation mixing, right? So how many decay channels there are?
Three, one for each generation?
Exactly, very good. So we have 3 decay channels. We call 3 decay channels. Basically, L can be electron, muon, or the tau, right? All of them, we said that the coupling constant is GW, right? Coupling constant. G weak, right? For each. Now we have to use the knowledge that the mass of the W is much greater than the masses of each one. So that means that I can neglect the phase space differences. And so I can write that gamma, right, of the leptonic channel would be proportional to 3G weak squared. That's easy. Now let's look at the hadronic. So hadronic W plus would go into a quark plus some sort of an anti-quark. Now naively, how many options do we have here? How many options do we have?
9.
9, right? You have 3 generations of quarks and 3 generations of anti-quarks. So naively, right, we can write down W plus would go into up, anti-down, up, anti-S, up, anti-B, charm, anti-D, charm, anti-S, charm, anti-B, and then T, anti-D, T, anti-S, and T, anti-B. Okay, but this is the naive. But now again, we look at the masses and we realize that the mass of the top quark is greater than the mass of the W. So the W cannot decay into anything that contains a top quark. And again, for all the other quarks, the mass of the W is much greater than the mass of the Q. If Q is different than top. So again, I can neglect the phase space. Right, so everything that includes the top is excluded. So we're left with W plus goes into up, anti-down, up, anti-S, up, anti-B, charm, anti-D, charm, anti-S, and charm, anti-B. So we're now left with 6 options. But now we can look at the CKM matrix, and that will tell us that transitions between the 3 and 1 and 2 are extremely rare. Right, 3 into 1 or 2 generations are rare, very rare. So we can neglect this decay into states that involve a B quark and some other quark with a different generation. Right, they never happen. So that means that I can neglect this. And we're left with only 4 options that we can expect to occur. U anti-D, U anti-S, C anti-D, and C anti-S. So we have 2 decays for the same generation, right? So this is the same generation, this is the same generation. So the coupling constants is G weak cosine theta Kabibo. And we have the 2 mixed generations. And of course, the coupling constant is G weak sine theta Kabibo. But we do have to remember that each of these quarks have 3 color charges. So we have to multiply by 3. But there are 3 colors for each quark. So overall, gamma, the hadronic, is 3 times we have 2 of G weak squared cosine squared theta Kabibo plus G weak squared plus sine plus G weak squared times sine squared theta Kabibo, which is 6 times G weak squared. So overall, we have that gamma leptonic into gamma hadronic is about 1/2. And indeed, when you look experimentally, right, about 11% of the W decay is into each of the leptonic flavors. Okay, into each leptonic flavor. And about 60%, 67%, it decays into hadronic. Now, by the way, if you think of it, you know, this experimental result now, this is an independent proof that there are 3 colors, regardless of anything else that we have. Right. This result independent proof of 3 colors. All right. This color charge. Questions? Any questions, everybody? No? Shocked? Okay, review this material. I'm going to give you a new problem set today. Yeah. Just review it, think of it. On Thursday, I'm going to start up discussing the Lagrangians of the standard model. It's going to be quite fun. We're going to speak a little bit more about gauges and where it comes from. I think it's really, really nice. I like it. So I hope you like it as well. Now I can do a stop sharing, I guess. I'm going to stop recording. And I very much